Thank you. Yeah, I want to thank Peter for his introduction. Okay, so I want to continue on a topic Peter discussed and a topic I discussed yesterday. But first I want to make a few general remarks. So what I did yesterday was that I look at spherical functions or so on the group and I wrote a differential equation for the spherical function on the group attached to some, so basically any spherical function is annihilated by some polynomial in Casimir, and then we wrote the differential equation. And there were two remarks. First of all, that we remarked that the spherical function f is completely determined by its restriction to A. This follows from Cartan decomposition. This has nothing to do with differential equation. The whole point of the calculation I was doing is to point out some formal statement of this type that omega applied to spherical function restricted to A. I mean, this is what I calculated. This is what I calculated at the end, but I was already over time, so I didn't want to dwell upon this, that this is given by applying certain differential operator, I think, let's call it R, I think, Nm, which depends, of course, of omega on f of A. This is definitely highly non-trivial that the action of the Casimir on the spherical function restricted is given by the action of an ordinary differential operator on A on spherical function, and this is called Nm radial part. I mean, you have to do some work. Why would even be there? This is definitely a map. Why would this be given by a differential operator? I mean, you have to do something. This is definitely not true in some kind of super generality. I mean, it follows from various things, and the argument I did was the stupidest one, is just to do the calculation. And if you do this calculation, what do you observe? Then, of course, one thing which also I was sloppy at the end, what Matvei pointed out to me, I am mapping A into complex plane by the map which sends an element A into alpha A, into evaluation of the positive root on our element A. So this is in coordinates t squared. So in rush I said that t is equal to z, but actually t squared is equal to z. And A corresponds then to positive real lines. So this is the identity in the group corresponds to point 1, and 0 corresponds to infinity in A, to minus infinity if you want in A. So behavior at infinity is given by the behavior of the solutions of these differential equations around the origin. What Peter was discussing, yeah. if I go to minus infinity I think, let me look, A inverse, I can write, this is the exponential of, say, t minus t. So the Lie algebra of this is a real line, and going to infinity corresponds to going to infinity in this parameter t. I mean, the Lie algebra is a line. And if I go to minus infinity, this A goes to 0, so t squared goes to 0. So, Harishchandra studied these differential equations in general by looking at Lie algebra coordinates. And then infinity is really at infinity. In these coordinates, at least one infinity, minus infinity in A, is at the origin. So it suggests to you that you should study the behavior of solutions at the origin. And this was observation Castleman made in general, and then using Deline's theory of equations with regular singularities or connections with regular singularities. So higher dimension and analog of Frobenius theory, you can actually understand the asymptotics. But basically, Harishchandra expansions is behavior of solutions in this disk. Because let me repeat this principle I mentioned during Peter's talk. If I know that this is system of, the equation Peter wrote, so the action of the Casimir is given by the second order differential operator with holomorphic coefficients everywhere except at 0, 1, and minus 1. So therefore, because the solution in the punctured disk can be given by a holomorphic function, and the equation he studied has a two-dimensional space of solutions given by multi-valued holomorphic functions on the punctured disk. Yes?
But you may have to take a branch.
I said multi-valued functions. And this, which makes sense on universal cover. And therefore, if I look at the restriction of the solutions to the real line, so positive real line, where they have meaning as matrix coefficients, this space is also two-dimensional, and just by dimension count, I see that any actual solution of the real equations extend to one of these holomorphic solutions. So, and using this holomorphic solutions, we prove the theorems Peter was quoting, so which explain how to solve this and how to get this expansions, Harishchandra's expansion at infinity. And I will discuss Harishchandra's expansions at infinity and their representation theoretic meaning in a moment. I just want to discuss briefly what is going at the origin, what Peter didn't mention in his talk. This is also a regular singular point. I even don't want to attempt to study the initial equations. If what you have learned from Peter's exposition that this is a mess, and that it's as good as it can be. I'm not willing to say anything more than that. But there is another important observation which says the following, that, this is a theorem, so I can look at the disk around 1, And the theorem is that if I write, this is what Peter was using when he was discussing recursion relations, if I write down formal solutions, so formal power series times logs, which are satisfied by differential equations. If I have a formal expression of the type he was writing, when power series are replaced by formal power series, I can still apply holomorphic functions, I can still differentiate, I can still check if those formal expressions are solutions. And the theorem is that those solutions converge. This is a big theorem, and the proof in this case is not very hard. You just count, and you see that the space of formal solutions is of the same size as a space of regular solutions, so every formal solution converges. This is the basic principle. Now, do we know one formal solution? If I have a Harishchandra module, do I know a formal solution for matrix coefficients in neighborhood of 1? Yeah, I mean, we can, matrix coefficients at identity are given by Taylor series. When we were discussing uniqueness, we proved that the Taylor series of matrix coefficients were given by a formula something like Tn over n factorials v twiddle pi x to the nv. I remember that we made some observation like this. This is a formal series. Because of the whole setup, this formal series, when we take x to be an element of Lie algebra of A, will be a solution here, formal solution, and this formal solution will converge. And then, of course, I have to deal with Cartan decomposition. There are some technical details in there, but basically you show that then there exists a spherical function which has this expansion. And this gives you, of course, you have to, this is the main idea, main observation Castleman made, that even in general, this singularity near identity is very complicated. It's not just a point. In general, your A maps into a quadrant, say in SL3R, you get a picture like this. So this is R square, and A in, say, SL3R, where A corresponds to these matrices. So this goes in positive quadrant in R2, embedded in C2. And as you can see, the singularity around identity, this is the singularity of your corresponding PDEs, is quite complicated. So analysis in this case is more complicated, but still the theorem holds. Any formal solution converges, and therefore, if you know the Harishchandra module, you can write a formal solution. This formal solution converges, gives you a spherical function. This spherical function gives you, when you vary n and m, or representations, gives you matrix coefficients. So in this way, you prove that the matrix coefficients exist. And of course, they are real analytic functions. I argue that these functions are real analytic except at the identity, which is the singularity of the equation. My argument doesn't work here, but for example, around this point, solutions extend to holomorphic solutions, so they're definitely real analytic on this interval. The Taylor series are convergent, but around 1, this is the theorem I was just saying. So you get that your matrix coefficients are real analytic. Therefore, the uniqueness part also holds. And we get the theorem which says matrix coefficients always exist. So this is the sketch of the proof of the statement. And as you can see, we really do not care very much about the explicit form of these differential operators, except we need to know where are their singularities and that those singularities are regular, so that they are not very bad. And this follows from the formula. But after we observe that, we can forget the formula. Yeah?
Matrix coefficients exist because we can solve the differential equation.
Yes.
But the solutions of the differential equation, they converge because,
this solution will converge. This is the only thing I'm claiming. So this is convergent. So I get matrix coefficients in some neighborhood, and then I have to do some work. But I mean, this is, I'm not, this is a sketch of the proof. I'm not, I mean, you just do a bit of extra work, and I mean, okay, if so around this point you have a regular point of your different. So if you get a matrix coefficient here, you can definitely do.
it's not clear to me why it converges, why this series converges, because
This is a formal solution of the differential equation. Because, I mean, this, I can write this down, and then from the properties of Harishchandra module, if you think, you will see that this expression will formally be a solution of this differential equation. Where,
the dimensions of the solutions of this and
no, I mean, just because of this differential equation was written down assuming as the existence of matrix.
formal solution, but why is it an actual solution?
Because I said because any formal solution converges. So this is, I'm using this deep statement about regular singularities to conclude that that formal solution converges. This is the essential step. If you don't like this, we are going to prove it. And several, I mean, there are definitely a number of competing proofs to prove this. If okay, so yeah. Okay. In this, I don't want to do this. I mean, I am willing to give a talk on regular singularities, because to understand regular singularities in some nice fashion, you have to look at the first order system on a punctured disk. Okay. And the second order, I mean, is what Peter was actually saying. I have z at 0, z prime plus p z I mean, let's see, y prime plus q z y equals 0. If I'm looking at, so 0 is a regular singularity if Q has at most pole of second order at the origin and P has a pole of first order. So our P and Q, if P and Q are regular, we don't have a singularity. If P and Q blow up, then they have to blow up mildly. And the condition is that just this is one way of looking at this. The other way is to look at that multiply by z square here, and then actually the condition is that this coefficient here vanishes at least at the same order as the derivative and this one here. So this is equivalent to the fact that this has a pole of second order and this has a pole of first order. If you have equation, and if you have the equation of nth order, then you just do the inductive definition. But the right way to look at this is to take a first order system on a punctured disk, and this is the statement that this function f is holomorphic in the full disk. So yes, I mean this is a first order system. If I say first order system, this means that Weismer is a column and f is a square matrix. But you see, if you remember your ODEs, then the one thing you should remember that if you have a differential equation of nth order, then you can write a corresponding system of first order equations, and if you convert this condition in this, you will get this statement over here. Yes. No, I mean, I'm still offering that I can give a lecture on regular singularities, but let's go back to representation. I don't think that I can write formulas on tacos. You see, now I'm just tempted to talk more about this, but this is a very beautiful piece of mathematics, because if you look at this equation, you have a solution here. So the idea is that you don't know anything about this solution, so you fool around the solution and you go around it, and you get so-called monodromy, and you understand what's going on there. And then when you understand the structure of the solution space of the system, when you allow f to have a singularity at 0, then you assume that the singularity is just the first order pole, which you get by division by this. And then you show that if you study the fundamental matrix, how it behaves when you approach the origin, you can estimate the growth, and the growth is moderate. So it grows like certain power of 1 over the distance from the origin. And this forces all the expansions Peter was talking about. So it's a very beautiful and simple idea, which in the case of differential equations of nth order, like this second order one, is kind of obscure, but for the first order system, it is simple and easy to track. If you look at my web page, if you really want to learn this, there are some notes I wrote several years ago for our standard course on complex analysis, which does this in complete detail and discusses formal solutions and convergence and blah, 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 all these things. Any other questions about this? Okay, so let me just finish this by one remark, which Peter alluded to. If you really struggle and study the initial equation at the origin, then what you conclude that there exists only one root which corresponds of the initial equation, which corresponds to regular solution. So the space of regular solutions are one-dimensional, and because the matrix coefficient for nn is, so I will remember, let's assume that pi v is an irreducible Harish-Chandra module. You write the initial equation, you see that there is one-dimensional space of solutions of your differential equations, and those solutions are non-zero at the identity, I mean, non-trivial ones. The zero solution, of course, is zero. And this tells you that if I fix, this is irreducible, so I'm looking at the differential equation f omega is, I don't know. So what did, Peter, you do? Lambda plus 1 square over 4 f, something like this. There will be one up to a scalar solution which is regular at identity for given lambda and for given n. This tells you, this is a differential equation proof of the statement Peter got by doing these calculations a couple of days ago, which says that if I fix a k-type, if I look at a Harish-Chandra module such that V is irreducible, Vn is non-zero, and pi omega acts, pi omega is equal to some fixed number, then there exists a unique Harish-Chandra module, irreducible Harish-Chandra modules with these properties. So you can prove this using differential equations for SL2. In general, this is hopeless because this singularity at 1 in general for arbitrary groups is much more complicated. So in a way, this is just a not very useful exercise in studying this singularity for matrix coefficients. But
Can you get an upper bound on the number of regular solutions that are regular at 1?
sure, I mean, you can get some, but it's not, I don't think you can get anything really useful what you cannot get, say, by simpler methods like D modules, by counting orbits. And I mean, I don't know, I never actually tried to get precise bound, but I don't think you can get anything really useful. Okay, so now let's look at Harish-Chandra expansions. Any questions about this? So you see, we have this long discussion last hour about solving this quadratic equation. What are the roots of initial equations? Are they plus or minus or lambda or mu and so? But the thing you should remember is just the following, that if I take any Harish-Chandra, and Peter, to simplify the differential equation, he didn't take this polynomial in account. If I put this polynomial, and this polynomial has degree 70, that our differential equation will have an order 140, and your initial equations will be a mess. But it will have finitely many solutions. So whatever you do, you get the following fact, that the matrix coefficient using Harish-Chandra expansion on A, so let me put this, so okay, now I want to, this is a power series expansion. Let me call this piece of A minus. A minus, this is very important. So A minus is the set of all elements of A such that A is bigger than 0 but less than 1. So this is this piece here. There, the matrix coefficient is given by Harish-Chandra expansion. And the only thing I care about is that these are some CLM, and I will put V twiddle V, and alpha AL log M alpha A. So what I'm doing now, see, in Peter's formula, he has this S's times power series. I'm writing power series like genuine power series. So there are finitely many M's. Integral M's, positive integers M's in this formula, but else look always like this, that L is some complex number K plus some N, which is a positive integer. So this is what you get, and the coefficients, of course, depend on V twiddle and on V. And now, these coefficients, vanishing or non-vanishing of these coefficients, carries some representation theoretic information. So we say that exponents of a vector V in Harish-Chandra module pi are just the set of all L's in C such that this CLM of, say, let's see how the, say blank V is non-zero for some M. So the set of exponents of a matrix coefficient is the set of all these L's which appear in this formula. And then I will take the union of all the exponents over the Harish-Chandra module and these are the exponents of a Harish-Chandra module, or of Harish-Chandra module V. And the theorem which Peter implicitly stated, I mean, this was this discussion about this S chi and is it finite and what this actually means at the end of the talk, is related to the following statement. So let me define a partial order on a set of complex numbers. So I will say that S is so greater or equal to t with this squiggly greater or equal if S minus t is a positive integer. So this is, I'll use this as the one. And let me denote, I mean, this is a set of complex numbers. And let me denote by exp of 0 of pi, of my Harish-Chandra module pi, the set of minimal elements of exp of pi. Minimal in the sense of this partial order. Why? This set is called the set of leading exponents of the Harish-Chandra module pi and v. You can say, why are these leading exponents? Let me remind you that here I'm going towards infinity, which is by going towards 0. So the worst behavior at the infinity will have these exponents. I mean, in this formula, my exponents here. So the smaller the guy is, this thing behaves worse if we approach 0. So the growth of or decay of matrix coefficient when I am approaching 0 is determined by these leading exponents. Does this make sense?
A quick question.
Yeah.
Any of these exponents, are they finite or infinite?
I mean, I'm going to make a statement now.
Okay.
I mean, the statement is, this is what Peter was hinting, that this set of leading exponents is finite and it's contained in the set, which basically is determined by the ideal in the center, which annihilates Harish-Chandra's module.
How about the two above it?
No, I mean here, of course, in general, these full power series, so you will have infinite sets. So just so this set is finite. And you can basically, from Peter's, a precise form of Peter's calculation is that if Harish-Chandra module is irreducible, you can have at most 2 leading exponents. And the precise formula for them depends on the solving this quadratic equation. Correctly, yes. But as we all know, quadratic equation has 2 solutions, and this is enough. So there are, for irreducible things, there are at most 2 leading exponents. So you can have either 2 or you have 1, and then you can have logarithms at the leading term. If you don't have, if you have 2, you can only have logarithms lower. I mean, possibly. Actually, you don't, but it doesn't really matter. Okay, so now the issue is what these guys are. Can we say something about this without solving even Euler equation? So let's talk about something totally different. Okay, before doing this, I think I want to introduce the following notion. I can look at my Harish-Chandra module, and I can filter it. So I can define Vk, where k is a positive integer, which is equal to the set of all v's in V such that the exponent of the exponents of the vector v are contained in the leading exponents of pi. I mean, this is some finite set plus k plus z plus. So this means that I am taking all the vectors such that in the expressions of all the matrix coefficients, these L's which show up at least k steps after the leading exponents. There is a simple lemma which I hope I will prove, but because I have just 20 minutes, let me just state it. It's a simple exercise which follows from the definition of matrix coefficients, which says the following, that Vk are decreasing family of, okay, let me put P. I have to tell you what is P. P, okay, it's A plus N. If I take A, the Lie algebra of Iwasawa A, which looks like this, and A is this, so I take this is what I denote by P. This is a subalgebra of SL2, which consists of all these matrices. So this is of P submodules. This is the first remark. So these are not modules for the full enveloping algebra, and but they are in action of any element of P maps V of k into V of k. And the second statement is that if I take element, say, y in N, then pi y maps V of k into V of k plus 1. So this is something which is important to prove, and actually very simple, follows directly from the definition of matrix coefficients. But let me just skip the proof for a moment. And another thing which follows from the very definition is that the intersection of all vk's, when k goes of all positive integers, is equal to 0. So these are decreasing subspaces which collapse to 0. Why is this so? If all vk's vanish, so how does the expansion of that? If we take v from the intersection, what can we say about the expansion of matrix coefficients? Yes, great. So here there are no coefficients. So this is a 0. I mean, all coefficients are 0, no non-zero coefficient. So this matrix coefficient is 0 for arbitrary v twiddle. So therefore, I can, because this is 0, it's 0 not only on A minus, on a full A, I can plug it 1. And this vector, if I apply any element of contragradient representation to this vector, I get 0. So the vector has to be 0. So this is the proof of this fact. So now remember this for a moment. So now let's talk about something totally different for a moment. If I take a vector in the intersection, then by definition, this vector if I put it here and take arbitrary v twiddle, all of these coefficients are 0. So its matrix coefficient on A minus is identically 0. So therefore, because matrix coefficients are analytic, it's 0 on a whole group. So in particular, it's 0 at identity. So, and remember, the value of the matrix coefficient at identity is with little v, and v twiddle is arbitrary, so this guy has to be 0. Agree? Okay. Okay, so now we will do something related to actually what we discussed during the break. So let me remind you what Castleman said, and we have this principal series. And of course, I don't want to get in. I have a bit more experience than Peter, so I don't want to get into trouble he got in. So I won't put modular function in the formula, as Castleman did. Just forget this delta. So I will write Frobenius reciprocity, because if I put delta in, all the formulas will be wrong. So, but basically what Castleman said is the following. If I look at Hom, okay, this is, I will call it, say, IND. This is a different functor without delta. And here I take Harishchandra module, and I want to, these are homomorphisms in a category of Harishchandra modules. My descript in sigma are the k-finite vectors of Castleman's principal series sigma delta p plus minus 1/2, or I don't know, something like that. But this is just the space of functions which look like this. I think he used chi, but this is the inducing representation. I mean, it's actually, as you will see, it's not. It just changes the formula. And then this is the same thing as Hom. And here, let me be fuzzy for a moment. So there will be actually P and something else. And then there will be V mod N, NV sigma. So I have to explain what this was the Frobenius reciprocity Castleman was discussing. So first of all, let me say something about this. This right side of the formula at the moment doesn't make any sense, because I have to tell you something more. First of all, I am assuming here that my V is finitely generated Harishchandra module. This means, if you want, or I can assume over U of G. I mean, this is not, I mean, I just don't want to make this confusing, but it doesn't make any difference, because if you take a vector here, this vector is k finite, so k cannot move it except in some finite dimensional space. So you can take finite generation in any way you want. You can take finitely many vectors which generate this as a Harishchandra module as a module over U of G. This is what the other thing is that from there is another lemma which we should prove at some point, but we didn't. This is a result due to Osborne, which says that in the case of SL2, U of G is equal to U of n times Z of G plus H times Z of G times U of K. Let me give you an idea which will allow you to prove this in 2 minutes. If you, first of all, we know from Poincaré-Birkhoff-Witt that U of G is U of n, U of A, U of K. Because remember, we had this x, which is a basis vector of k, we have h, which is a basis vector of a, and we have y, which is a basis vector of n, and monomials in those vectors form a basis of the enveloping algebra by Poincaré-Birkhoff-Witt, and they also form the basis of these factors. I mean, this just means that any element here can be written as a product of elements from these guys. Then remember, the center is generated by a Casimir, and we have this formula that omega is h squared minus h minus y and y bar. So this y is here. So, and because Casimir involve h star, this is why I have to have this h over here. So basically, you use the formula for the center using Casimir, you get this junk which goes over here, and then you fiddle a little bit by doing the induction in the order of elements in Poincaré-Birkhoff-Witt basis, and you can prove this statement. I mean, it's not completely trivial, but relatively easy exercise. So if you think about this, you'll easily figure out how to prove. So what is the consequence of this? Let me assume that I have a finitely generated Harishchandra module. This means that I can pick finitely many vectors, that V is equal to, I'm running out of time, U of G Vn, say sum, and goes, Vi, I goes from 1 to n. These vectors are k finite, so the enveloping algebra of k can move them around only in a finite dimensional space. So by increasing a number of these guys, I can, but still keeping infinite, I can get rid of this guy. Then I have center of the enveloping algebra. Remember, in any Harishchandra module, this guy moves the vectors still in finite dimensional subspace. Any vector is ZG finite. So this, again, increases the number of the vectors I need to span the generating subspace, but it's still finite dimensional. H just moves, it's one element of the Lie algebra, it moves that subspace somewhere else. And then I have this piece without H, so I can possibly double the number of generators, but not more than that. And then I have to apply UN. So what is the upshot of this discussion? Any finitely generated Harishchandra module is finitely generated as U of n module. So this is the consequence. This is actually what Osborne claimed, that if you take a finitely generated Harishchandra module, then it's finitely generated as U of n. So if my V is finitely generated, how big is this quotient? This is the quotient of all the vectors I get by applying a copy of n. So I can write V as the sum U of n, say W I goes from 1 to some m. Excuse me? No. Remember, U of n is C plus Cy plus Cy squared and so on. You're close. It's finite dimensional. Yes. You thought right. You just misspoke. Yeah. So this is a finite dimensional. It could be 0. It could be 0, but it's actually finite dimensional. Because it's finite dimensional, then actually one can easily check that this representation of P can be extended to the representation of the group. So these are real group P homomorphism. P is this group plus minus, this is the subgroup of SL2 consisting of these matrices. And of course, sigma, because this was induced representation, is a representation of P, so this thing makes sense. Okay, so now there is the most important thing, but I'm also running out of time. So now remember, we want to prove that there is this subrepresentation theorem proved by Castleman, which says that any irreducible Harishchandra module is a submodule of certain principal series module. So to prove this, we have to prove, it's enough to prove that this is non-zero for some sigma. Because if this is irreducible and this is non-zero, I have a morphism. The kernel of this morphism is a submodule. Because the morphism is non-zero, the kernel cannot be everything. So the kernel has to be 0. It has to be injective. So I have to show that this is non-zero. And to show that this is non-zero, it's enough to show that this is non-zero. But to show that this is non-zero, I have to show that this thing is non-zero. Because this is finite dimensional, I have a finite dimensional P module. It will have an irreducible quotient. Take any maximal submodule, quotient with it, and call quotient sigma, and the quotient map will be a non-trivial element here. Is this clear? So it's enough to prove that it's enough to prove that V mod NV is non-zero. This means that NV is different from V. Why is NV different from V? Because we can prove, and I should tell you a few words about these things in another lecture, but there is a simple lemma which says that Vk contains nkv for any k in Z plus. So now, because these Vk's are shrinking to 0, then NKVs also have to shrink to 0, so we cannot have the equality. This equality would imply this, and then, of course, this would contradict this lemma. So, you see, using asymptotics, you can show that this family of completely algebraically defined subspaces, which are also P modules. There are a lot of parallels between those two things, which I hope we are going to discuss in future, but I'm over time, so I don't. So these are all P modules. And these P modules, this decreasing family of P modules is completely algebraic, but as this relationship suggests, this family of P modules is closely related to the analytic problems, analytic properties of Harish-Chandra modules. And this was a conjecture of Castleman that actually one can read off all the full Harish-Chandra expansions by studying the properties of this filtration. And this was proved by Hecht and Schmidt that actually this conjecture is true. So basically this filtration given by of the Harish-Chandra module given by these NKVs recovers all the properties of Harish-Chandra expansion in some sense. But I mean, this is all related to the stuff we are going to discuss in future. And everything I said here holds in a full generality. The things you should remember that from the asymptotics, we conclude that every irreducible representation is a subrepresentation of principal series, which was proved by brutal computation by Peter, just by listing all irreducible Harish-Chandra modules, showing that they sit in some bigger modules, which then Castleman proved Harish-Chandra modules of principal series yesterday by this calculation. This is one thing. The other thing is, and I mean, let me just finish with this, because I promised this 1 hour ago, and let me keep the promise. So what you can say about, so V and V, of course, because of this thing, projects onto V mod V1. So so this is finite dimensional. How A acts here? A acts here as, if you look at the definition, by leading exponents. Why? Because this is essentially what we get from Euler equations. The vectors which are here start in their matrix coefficient expansion, not by a leading exponent, by the next guy, because of this shift by 1. So you can read off leading exponents from this quotient, and those leading exponents correspond to the action of A in this V mod NV, which is finite dimensional. And actually, there is a sharper result, which I proved long time ago, that is I can look at all A weights in this space, which is completely algebraic. This is 0n homology of this module. I can look at minimal exponents with respect to this partial ordering we define, and those minimal exponents are just the leading exponents of the Harishchandra module. So basically, this tells us that leading exponents of the Harishchandra module can be read off from the 0n homology. From this space. And one can show, so this is why I was saying that in Peter's calculation, this quadratic equation was irrelevant. For an irreducible Harishchandra module, if you are just using this Orsborn lemma a little bit more precisely, you can show that your n homology is at most two-dimensional, and it will have weights which are just given by the formula Peter was trying to get. And from this, you can find what are leading exponents without worrying about the initial equation. Okay, so this is, I am 5 minutes over time, so this is a place to stop. Any questions?
Since you said the word n-homology, can you just say what?
No, n-homology, okay, I misspoke. This n-homology, this is usually denoted by H naught of NV. This is, usually this is so-called 0n homology, and there are higher Lie algebra n homologies, which are derived functors of this functor, and this is, this requires another lecture, which maybe we are going to have. You can write this as C tensor over U of n with V, and these higher n homologies are just stores of this. So depending on your knowledge of homological algebra, you can interpret this any way you want. For the purpose of today's lecture, you can think of this. I was not thinking. You can think of this just as this object.
So by n-homology, you mean the Lie algebra homology?
Yes, yes. Yeah, 0, this is 0 Lie algebra and homology. Yes, you're right. Okay, so speaking about this, how many of you know something about homological algebra? Okay, great.